Good morning, students. Welcome to the sixth session of AC circuit, that is module 2 of basic electrical engineering, ES-EE101. In this session, you are going to learn the concept of parallel resonance, okay, and the concept of real power, what is reactive power, the concept of power triangle and power factor, and then based on these topics we will solve some numericals which will help you to understand how to solve the problems, okay. And at the end of the class I will give you some assignments, okay, which you have to try to solve it. So before starting today's topic, that is parallel resonance, let's solve the previous assignment which was given in previous class. The question given was a 50 ohm resistor, a 20 millihenry coil and a 5 microfarad capacitor are all connected in parallel across a 50 volt 100 hertz supply. Okay, calculate the total current drawn from the supply, the current for each branch, and the total impedance of the circuit and the phase angle, and also construct the current and admittance triangle that represents this circuit. Okay, so what are the important terms that was included in this question? The resistance value, inductor value, that is 20 millihenry, capacitor value 5 microfarad, and most important thing is frequency, that is 100 hertz, and 50 volt is the voltage source. So since voltage is common here, so our reference will be here our voltage, and we can calculate the current in each leg very easily. How? This resistor is connected across 50 volt, correct? So IR you can calculate, L value you also know. So you have to find out first XL. Why? Because L value is in Henry, so you have to convert it in ohm. Similarly, here capacitor value is given, so you have to calculate the XC in ohm. Okay, so let's solve these two things first. That is inductive reactance XL, that is XL equals to omega L 2 pi F into L. What is F value? F is the frequency, that is 100 hertz, correct? So 2 pi into 100 into 0.02, that means 20 millihenry. So the final value of XL is 12.6 ohm. Fine. Next, calculate the value of XC, that is 1 by omega C. So its value is 318.3 ohm. Now calculate the impedance. How? Since these are in parallel, so our formulation is like this: 1 by Z equals to 1 by root under of R square, 1 by R square, okay, plus 1 by XC minus 1 by, this is our C, 1 by XC minus 1 by XL whole square. Here XC value is larger than XL, okay. So if there is XL value is larger than XC, then either way is correct, because whether it is negative or positive, the square of that term will always become positive, okay. So if you write this thing as 1 by XL minus 1 by XC, it will give you the same answer, okay. Now calculate the impedance of this circuit. This is the equivalent, right? So value is 12.6 7 ohm. Now, whatever value you had calculated here, this is your magnitude. Okay. Now, the current through the resistor, you can calculate V by R, that is 1 ampere. The current through the inductor is V by XL, that is 3.9 ampere. Okay. Whatever value you are calculating here, all are magnitudes. Okay. No angle is calculated here. Now, the current through the capacitor, that is 0.16 ampere, V by XC, put the values. Okay. So, what is the total current? Total current, either you can calculate like this, IR square plus IL minus IC whole square and 3.87, or the equivalent impedance you already had calculated, that Z value you already know, right? What is the value? 12.7. Okay, Z value is 12.7 ohm and V value you already know, that is 50. Okay, 50 volt. So you can calculate like this also, IS equals to V by Z. Both are equally correct and you will get the same value here. Clear? Now, what is the conductance? Because we have to calculate the admittance triangle. So for admittance triangle, you need to find out the conductance, the susceptance, okay, and finally the Y, admittance. So what is conductance? Conductance is the inverse of the resistance. So 1 by R, that is 20 millisecond. What is inductive susceptance? That is BL, 1 by XL, that is 80 millisecond, and millisiemens. This is S. Okay. This unit is Siemens, SIEMEN. That is not second, that is Siemens. Okay. Next is capacitive susceptance, that is B suffix C, and that value is 3 millisiemens. Now, admittance value is Y equals to 1 by Z. Z value you already had calculated earlier. So, just by doing inverse, 78 millisecond. So, what is the phase angle? First, draw the admittance triangle. This is your G, correct? This is your BL minus BC, and you will find out the Y value by Pythagoras theorem. Okay, and this is the current and voltage related phasor diagram. Here you can see that voltage is here because this is common to all the elements. So IR, IL, IC will be placed, and V is our reference for the current flowing through the resistance. IR will be always in phase with the voltage, that is 1 ampere, correct? And IC, that means current flowing through the capacitor. When current flows through capacitor, current always leads the voltage. So as you can see, this is leading the voltage by 90 degree. And for inductor, voltage always leads the current. So here voltage is our reference, so current will be lagging. You can see that current is lagging here. Okay, now IL minus IC, that is your resultant current in y-axis, that is here is minus y-axis. Now by doing Pythagoras theorem, you can calculate the total current that is flowing from the source. Okay, so this is our current triangle, this is our admittance triangle. Okay, so that's how step by step you need to calculate. Okay, so now let's start today's topic, that is parallel resonance. In many ways, a parallel resonance circuit is exactly the same as the series resonance circuit. We looked at it in previous tutorial. Both are three element networks that contain two reactive components. What are the reactive components? That is L and C, that is inductor and capacitor, making them a second order circuit. Both are influenced by variations in the supply frequency, and both have a frequency point where their two reactive components cancel each other out, influencing the characteristics of the circuit. Both circuits have a resonant frequency point. Now, what is admittance? That is the inverse of the impedance of the circuit. That is Y equals to 1 by Z equals to root under of G square plus B square. What is G? That is conductance. And what is B? B is our susceptance. Now, where there is two types of element, that is inductor and capacitor, two types of susceptance will be there. One is inductive susceptance, another one is capacitive susceptance. Correct? Now, a parallel resonance circuit stores the circuit energy in the magnetic field of the inductor and the electric field of the capacitor. The energy is constantly being transferred back and forth between the inductor and the capacitor. That results in zero current and energy being drawn from the supply. Here, in the solution of AC parallel resonance circuit, we know that the supply voltage is common for all the branches. That means V is our common. That's why it is taken as reference for parallel circuit. Clear? So this can be taken as our reference vector. As said, each parallel branch must be treated separately as with series circuit, so that the total supply current taken by the parallel circuit is the vector addition in the individual branch current. Okay. The admittance of the parallel circuit is given by Y equals to G plus BL plus BC. These are all vectors, right? Now, this thing is converted into complex formation like this. Y equals to 1 by R plus 1 by J omega L plus 1 by plus J omega C, or we can write it like this. Correct? Put the value J here. Fine. Now, the resonance occurs. What was the condition? That the total imaginary term must be equals to 0, or the inductive reactance must be equals to the capacitive reactance. Here also you can see that for this LC part, XL equals to XC. Okay, so that's how the imaginary term will be 0 in Y, because see here in Y formation or equation, if we are telling that we need to put 0 for the complex term, then this part will be equals to 0, right? So there you can calculate also the frequency. So frequency will be same 1 by 2 pi root LC. So this is called the resonant frequency. And if 2 pi is multiplied, then it is called the angular frequency at resonance. That is equals to 1 by root LC radian. Correct? Now, what will happen if resonance occurs in this parallel circuit? Here, when XL cancels out the XC, you can see that this term will be 0, and so Y at the time of resonance will be equals to 1 by R. That means in the total circuit only resistance will be present. So other circuit will be the open circuit. Correct? Here you can see that this is our open circuit. Fine. So only R is present. So likewise, when the series connection occurs, there also the circuit becomes short because XL equals to XC. So only R is taking part for current during the current conduction. Here also the R is taking part for the current conduction. Clear? So the circuit is totally resistive in nature. All the reactive current is 0. That means IL and IC are both 0. Now, At resonance, the parallel LC tank circuit acts like open circuit with the circuit current being determined by the resistor R only. So the total impedance of the parallel resonance circuit at resonance becomes just the value of the resistance, as I said. Okay, so I hope this curve is familiar to you, just like the series circuit, correct? This is the peak value and it is called the dynamic impedance. Okay, now this is the Z value maximum. Okay, fine. Next is current in the parallel resonance circuit. In parallel resonance circuit, the total circuit acts as the only resistive nature. So as the total susceptance is 0, the resonance frequency, the admittance is at its minimum and it is equal to the conductance G. Therefore, at resonance, the current flowing through the circuit must also be at its minimum, as inductive and capacitive branches are equal. That means IL is equals to IC and both will cancel out each other and are 180 degree out of phase, right? Now IR equals to V by R, IL equals to V by XL, that is V by 2 pi FL, IC equals to V into 2 pi FC, correct? So I total you can calculate. If the whole system is not resonant, then IT will be like this. Fine. Now what is the quality factor? While this resonance occurs, this is R by 2 pi FL, that is just the inverse, that is R root under of C by L. Okay. Now the power in AC circuit. The electrical power is the rate at which the energy is being consumed in the circuit. As such, all the electrical and electrical components and the devices have a limit to amount of electrical power that they can safely handle. Just like the electric bulb, a wattage is written on the glass, that is either 20 watt or 40 watt or 10 watt. What is that watt means? That watt means that it will consume 20 watt active power. Okay. Now, electrical power can be time varying either as DC quantity or as an AC quantity. Okay. The amount of power in a circuit at any instant of time is called the instantaneous power and is given by a well-known relationship of power equals to volt into current. That is, voltage into current will give us the power. So as you can see here in this waveform, this is our AC circuit. Okay. Now AC circuit, and it is the power consumed. That is the power consumption. Okay. That is V into current. This is our current. Okay. So at any instant, suppose we are taking this instant or this instant, whatever power it is consuming, it is called the instantaneous power. Okay. Now, here, if DC quantity is there, then DC means constant voltage and current is also constant, correct? So, just V into I, it will give us the constant power, just like this. Okay. Now, what is real power? Real power is known as the true or active power that performs the real work within an electrical circuit. The real power is measured in watt, W-A-T-T. Okay, and it defines the power consumed by the resistive part of the circuit. That is also can be measured in kilowatt or megawatt. Okay. Now, actually, a power whatever we are calling power, the power is first apparent power, that is called S. Okay, this apparent power is of two types. One is active power or real power, right? Another one is reactive power. So what we are discussing here, that is the active power or the real power, right? Which is the real consumable power. That is the reactive power. Okay, we will discuss this reactive power later. Now, what is active power? Suppose in this is a resistor through which current I is flowing and voltage developed is V. Correct? Now, according to Ohm's law, V equals to IR. Correct? Now, when current is flowing through the resistor, whatever energy is produced, that is dissipated as heat. So that is the active power, which is I square R. Okay. So this heat energy is the active power and that amount is I square R. Correct. Now, here V and I both are in same phase, as you already know. And now in the AC circuit, this is our V and I. Correct. So the total power consumption is determined by V into I cos theta. Why? Because V is here, okay, and I is also here. So whatever power we are taking here, okay, that is our active power, right? And reactive power is always in either positive y-axis or negative y-axis. This is our active power, correct? And this is our reactive power in y-axis. So if you do the Pythagoras theorem, you will get the apparent power. Okay, so this is our total apparent power. So apparent power S is called as the multiplication of V into I. Correct? Now here it is making some angle theta. Correct? So what is our active power? That is S into cos theta. That means V into I into cos theta. So this P is equals to, that is active power is VI cos theta. If we multiply V into I, whatever power we are calculating, that is called the apparent power. Okay. Now its workable unit is called, workable component is called the active power. That is the cosine component of the apparent power. Correct? Now for only the resistor, this theta is 0 because there is no angle difference between V and I. So at that case, for the resistor, there is no angle difference between V and I, right? No phase difference. So phase difference is theta is 0. So cos 0 degree is 1. So our P will be equals to V into I. Correct? Now this is the power waveform for AC circuit. You can see it. Okay. This is our active power consumption. Correct? Now the reactive power, as I already said you, the S is our apparent power. It is of two types. One is active power, another one is reactive power. Okay. Now this reactive power is of two types. One is capacitive reactive power, another one is inductive reactive power. That means the reactive power when current is flowing through the capacitor, and when the current is flowing through the inductor, that is called inductive reactive power. Okay. Now, reactive power, sometimes called the wattless power, because it is not consuming any power, it is not used for any working purpose. Okay, is the power consumed in AC circuit that does not perform any useful work but has a big effect on phase shift between the voltage and current waveforms. Okay, reactive power is linked to the reactance produced by inductors and capacitors and counteracts the effect of the real power. The reactive power does not exist in DC circuit. Why? Because there is no phase difference, and DC circuit, the V, the voltage and current waveform is always constant with respect to time. That is not alternating in nature. Clear? So, this is our active power. Okay, this is our reactive power in y-axis. So what is our total apparent power? This, correct? Now this S and this angle is theta. So sinusoidal component of this S is called the reactive power, correct? According to trigonometrical rule. So V into I into sine theta, because S is equals to V into I, correct? So V into I sine theta. When there is only inductor, then the angle difference or phase difference between voltage and current is 90 degree for pure inductor. So for only L present in the circuit, the angle is 90 degree, right? So sine 90 is 1. So V into I, VAR bar. Okay. Now, when only C is present, then what will happen? Then this angle is minus 90. Then this will be minus 1. Okay. So simultaneously the sign will change and the all system will change. Here it is written QL, where only L is present in the circuit. When C is present, it will be written as QC. Okay. Now this is the power consumption that is also alternating in nature. You can see it is negative power, it is positive power. So it is alternating in nature. Correct? Now, as I said earlier, for only capacitor, that is minus angle is minus 90. So your total QC, that is capacitive reactive power, is the minus V into I VAR. Okay. So here you can see the waveform and everything. Clear? Here is the phase difference, that is theta for pure inductor, which is nothing but 90 degree. Correct? Which one is leading? Current is always leading for capacitor. Right? So this is minus 90 degrees. So finally QC equals to minus V into I VAR. Now what is apparent power? This is a mathematical relationship between real power and reactive power called the complex power. The product of RMS voltage V applied to an AC circuit and the RMS current I flowing into the circuit is called the volt ampere product, or VA, which is called the apparent power, that is S, whose magnitude is generally known as the apparent power. This S is a complex power. Why it is called as complex power? Because it is the imaginary axis or y-axis, right, in complex notation, and this is the real part, real axis, it is P and this is Q. So we can write this S as P plus JQ, right? So this is the complex notation. Okay, And if we want to write it as the polar notation, then this will be mod S angle theta, right? What is mod S? Mod S is nothing but root under of P square plus Q square. And what is the angle? Angle is the tan inverse Q by P. Clear? Now, as the apparent power is made up of two parts, resistive power, which is in phase power or real power in watt, and the reactive power, which is out of phase power in volt ampere reactive, which we can show that vector addition of these two power component in the form of power triangle like this. Okay, so either you can write this angle as phi or theta. That is nothing wrong. There is nothing wrong. Okay. Now, what is real power? That is P equals to I square R, right? What is reactive power? That is I square X volt ampere reactive. That is watt, and apparent power is called I square Z. So this power triangle, it is called the power triangle. Okay. Now, this power triangle is almost similar to our impedance triangle. This is our R, this is our X, and this one is our Z, and this is again the same angle, either phi or theta. Clear? Now, what is power factor? This power factor is an important part of an AC circuit that can also be expressed in terms of the circuit impedance or circuit power. Power factor is defined as the ratio of real power to apparent power and its cosine term. Okay. Now, this is generally expressed in either decimal value, that is real power in equals to apparent power into power factor. So here you can see this is the angle. Okay. So cosine of the angle is called the power factor, either cos phi or cos theta, whatever notation you want to use, you can. So cos phi, cos theta, it is called the power factor. Okay. So what is cos theta? Cos theta is the ratio of P to S, right? The power factor is written as their phi angle is given, so either cos phi, or you can write as cos theta also. That is nothing but the ratio of real power to apparent power. Okay, so this thing you need to remember. Now, next we will solve some numericals. A series resonance network consisting of a resistor 30 ohm and a capacitor of 2 microfarad. This is microfarad, okay, and an inductor of 20 millihenry is connected across sinusoidal supply voltage, which has a constant output of 9 volt at all the frequency. Okay. Now calculate the resonant frequency, the current at resonance, and the voltage across the inductor and the capacitor at the resonance, and also find out the quality factor. So what is given already? L value, C value already given. So you have to find out the frequency that will cause the resonance. So what is the resonance frequency formula? Fr equals to 1 by 2 pi root LC. L value is 20 millihenry and C value is 2 microfarad. What is 2 microfarad? 2 microfarad means 2 into 10 to the power minus 6 farad, and it is 20 millihenry. That means 20 into 10 to the power minus 3 Henry. Right? Put all these values, you will get the resonant frequency value, that is 796 Hertz. Now, at resonant frequency, the XL and XC is always equal. So, these imaginary terms cancels out each other, and At resonant frequency, this circuit will act as the resistive nature, right? So what is the current value, current magnitude? That is V by R, that is 9 by 30. So it is 300 milliampere. Clear? Now, what is the inductive reactance at resonance frequency? You already know. F value is 796 and XL equals to 2 pi FL. So put the value of F and L. The value is 100 ohm. So without calculating anything, you can also say that this thing is equals to XC, right? In ohm. So what is the voltage across the inductor and capacitor? VL equals to VC, also at resonance. That's why it is becomes short circuited, and the only R is playing the role there. So VL equals to VC, that is VL equals to I into XL, because XL value is calculated, or XC value, both are same. Multiply this, you will get that VL value is 30 volt. Okay, so what is the quality factor? Quality factor is the ratio of the inductive reactance to the resistance. So 100 by 30, that is 3.33. Okay. Now, question number 2. A parallel resonance network consisting of a resistor of 60 ohm and a capacitor of 120 microfarad and an inductor of 200 millihenry is connected across a sinusoidal supply voltage, which has a constant output of 100 volt at all frequencies. Calculate the resonant frequency and quality factor. So, same way, find out the resonant frequency. FR value is 1 by 2 pi root LC. Put the L and C value. L value is given 200 millihenry. That means 0.2 Henry. And C is 120 microfarad. That means 120 into 10 to the power minus 6. Right? So, finally, FR value you will get as 32.5 Hertz. Now, inductive reactance calculated by this formula 2 pi FL. So XL value is, putting the value of F, you will get, this is 32.5, okay, this is 0.2, so it will be 40.8 ohm. Now what is the quality factor? Here, unlike the series resonance circuit, it is the inverse. Okay, that means R by XL, so it will give you 1.47. Now, total circuit current at resonance will be equals to the V by R, because whole circuit becomes resistive in nature, because Y is equals to 1 by R only. Clear? So, IT equals to IR equals to V by R, that means 100 by 60, because R value here is already given 60 ohm. So 100 by 60 means 1.67 ampere. Now, next numerical, a wound coil that has an inductance of 180 millihenry and a resistance of 35 ohm. Here you can see 180 millihenry and 35 ohm is connected to a 100 volt 50 hertz supply. See this frequency, okay? Calculate the impedance of the coil, the current, the power factor, and the apparent power consumed. Also draw the resulting power triangle for this system. Okay? So first, the impedance of the coil you have to find out. What is the impedance of the coil? That is Z equals to, in complex formation, R plus JXL, right? So, in polar formation, this will be R square plus XL square root angle theta, right? What is theta value? Theta is tan inverse XL by R. Clear? Now, this L value is given here 180 millihenry. So frequency is given 50 Hertz. So find out here the XL value, right? So let's see impedance of the coil, that is R equals to 35 ohm. XL value is calculated 56.6. So Z value is given. So whatever Z value calculated here, that is the modulus value. So what is the final Z value? Z value will be 66.5 angle tan inverse 56.6 divided by 35. Okay, so it is the final value. If you have calculated, you can find out the angle of theta easily. Okay, what is the current consumed by the coil? What is the current consumed? That is V equals to I by Z. Okay, so I equals to V by Z. Here V is 100. That means it is your 100 angle 0 degree in complex notation. Okay, if only magnitude is required, then you can simply follow this formula V by Z. Okay, but if the phase difference you want to calculate out from V to I, then use this polar notation, okay, or complex notation as you can. So here 100 angle 0 degree and this one is 66.5 angle theta. So 1.5 angle minus theta. So it is the complete answer for I. Magnitude is 1.5 and angle is minus theta. Okay, that means this in this circuit with respect to voltage, V is our 0 degree here. Okay, V is 0 degree here. With respect to V, I will always be lagging in condition by angle theta. Okay, fine. So what is the power factor? Power factor you can calculate as cos theta. So either you find out the ratio of R by Z, or here you can find out the angle theta. So just cosine of this angle will give you this. Okay, so the total system is lagging in nature. So it is matching with your concept, that is, if inductor is present in the circuit, the voltage will always lead the current, or current will always lag the voltage. Clear? What is the apparent power? First, calculate the active power, P VI cos theta, Q VI sin theta. Put all these values in Pythagoras theorem and you will find out the S. Or just voltage value you already know, and current value you also know. Just multiplying those factors you can calculate the S value also. So either way you can solve it. Clear? So this is the power triangle and this one is the angle theta, that is 58.2 degree. Clear? So that's for today's session. I hope no assignment today is given. Just read all these things. Okay. So until next session, thank you.